For centuries, humanity has pondered its past, often viewing ancient eras as primitive. However, recent archaeological revelations consistently unveil a different story, one of profound ingenuity. Civilizations long vanished developed technologies that challenge our modern perceptions of their capabilities. These discoveries compel us to scrutinize the true origins of scientific thought and practical application, transforming our understanding of antiquity. Many believe technological progress is a steady, upward climb, with each era superior to the last. Yet, evidence suggests peaks and valleys, with certain ancient societies achieving stunning advancements. Their knowledge, often lost or rediscovered centuries later, indicates a more complex historical narrative. We find ourselves asking, how did they manage such complexity without our modern resources? This exploration delves into Tecnologia Antiga e Civilizações Perdidas, uncovering engineering marvels and scientific breakthroughs. We will examine how ancient cultures, without our modern machinery, constructed astonishing structures and devised intricate mechanisms. Our focus will remain firmly rooted in verifiable archaeological evidence and rigorous academic interpretation, avoiding sensationalism. The objective is to understand their methods. From astronomical calculators to incredibly durable building materials, the innovations are diverse and profound. These societies often possessed a deep understanding of physics, mathematics, and metallurgy, applying principles we consider contemporary. Their achievements were not accidental, but the result of systematic knowledge, accumulation, and ingenious problem-solving. This depth hints at lost wisdom waiting to be appreciated. Join us as we journey through time, unearthing the forgotten brilliance of civilizations like the Romans, Egyptians, and others. We will meticulously analyze the evidence, contextualize their societies, and understand the limits of our current knowledge. What can these ancient engineers and scientists teach us today? And what secrets still lie buried beneath the sands of time, waiting for discovery in resilient materials? One profound secret lies within Roman concrete, a material whose longevity often surpasses modern counterparts. The Pantheon and numerous aqueducts stand as testament to its enduring strength, resisting millennia of seismic activity and corrosive marine environments. Modern science is only now fully unraveling the sophisticated chemistry behind this remarkable ancient innovation, providing crucial insights into its unparalleled durability. Archaeological analysis reveals that Roman concrete, known as opus cementitium, utilized volcanic ash, pozzolana, mixed with lime, rubble, and seawater. This specific combination created a binding matrix fundamentally different from contemporary Portland cement. The discovery of aluminum tobermorite and strontium-rich philipsite crystals forming over time within the material explains much of its self-healing capability, actively strengthening the structure. Historical texts, particularly those of Vitruvius, provide context for these engineering practices. Roman engineers understood the importance of material selection and mixture ratios for specific applications, whether for underwater structures or massive dome construction. Their empirical knowledge, refined through generations, represented an advanced understanding of material science, unparalleled for nearly 2 millennia after their decline. Scholarly theories suggest the long-term chemical reactions between the pozzolana and seawater were key. Unlike modern concrete, which degrades over centuries, Roman formulations actually grow stronger, forming new mineral phases. This process effectively seals cracks, preventing water penetration and subsequent structural decay, a living material principle our ancestors intuitively grasped through experimentation and observation. However, replicating Roman concrete perfectly today remains a challenge, partly due to proprietary ancient techniques and specific local materials. While we understand the core components, the exact thermal curing conditions and specific mineralogy of their source materials are still subjects of ongoing research. This gap highlights limitations in our knowledge, yet underscores their unique mastery of these tecnologia antiga e civilizações perdidas. But how did other ancient cultures manage water with equal ingenuity? Beyond durable structures, ancient civilizations exhibited astonishing prowess in water management, crucial for survival in diverse environments. The Nabateans, flourishing in the arid deserts of modern-day Jordan around 400 BCE, transformed their parched landscape into a verdant oasis. Their elaborate systems of dams, cisterns, and terracotta pipes collected every drop of rainfall, directing it to their capital, Petra, and supporting extensive agriculture. Archaeological excavations at Petra reveal sophisticated hydraulic engineering feats, including gravity-fed aqueducts carving through mountains and underground reservoirs capable of storing millions of liters. These structures demonstrate an advanced understanding of hydrology and geology, meticulously designed to minimize evaporation and purify water. Their engineering ensured a consistent supply for a thriving urban center and caravan trade routes. Historically, the Nabateans were not just traders but master engineers, applying their knowledge to harness scarce water resources. Their methods allowed them to flourish where other cultures struggled, establishing control over vital trade routes. This strategic use of tecnologia antiga e civilizações perdidas in water conservation underpinned their economic and political dominance for centuries, a testament to resourcefulness. Theories suggest the Nabateans developed their systems through generations of observation and experimentation, perfecting techniques passed down orally and through apprenticeship. Their capacity to identify subtle geological features conducive to water collection and their precise masonry for watertight structures reflect a scientific approach. They engineered solutions specifically tailored to their harsh environment, ensuring sustainable growth. Despite the grandeur of their achievements, precise details of their planning processes or theoretical underpinnings are limited, relying heavily on material evidence. We lack comprehensive written records detailing their engineering manuals. This absence highlights the interpretative challenges in fully comprehending their methodologies. Yet, their legacy invites comparisons to even earlier, equally impressive urban water systems, like those of the Indus Valley. The cities of the Indus Valley civilization, particularly Mohenjo-Daro and Harappa, thriving around 2500 BCE, present an even earlier and equally remarkable example of advanced urban planning and hydraulic engineering. Their meticulously planned grids, standardized brick sizes, and intricate drainage systems were unparalleled for their time, predating similar advancements in Mesopotamia and Egypt by centuries. Archaeological excavations reveal an astonishing level of civic organization. Mohenjo-Daro featured advanced public baths, individual homes with private wells and bathrooms, and highly efficient wastewater disposal systems. Elaborate covered drains, often two-tiered and incorporating manholes for maintenance, ran beneath the streets, channeling refuse away from residential areas to distant disposal points. From a historical perspective, these cities demonstrate a centralized authority capable of executing massive public works projects. The uniformity of infrastructure across different sites suggests a shared cultural understanding of urban sanitation and public health. This comprehensive approach to city living showcases an advanced society prioritizing cleanliness and systematic design, a hallmark of their Tecnologia Antiga e Civilizações Perdidas. Analysis of the drainage systems indicates a sophisticated understanding of gravity and fluid dynamics. Sloping channels, carefully constructed ceramic pipes, and sealed joins prevented leaks and blockages. Theories propose that this emphasis on hygiene might have contributed to the long-term stability and health of their urban populations, reducing the spread of waterborne diseases in densely populated areas. Despite the rich archaeological record, the exact mechanisms of their urban governance, and the specific engineers behind these designs remain unknown. The Indus script is largely undeciphered, leaving gaps in our understanding of their administrative and technical literature. This limitation means we infer their knowledge primarily from their impressive material remains, prompting us to examine other ancient marvels with similar precision, yet different applications. Shifting our focus from civil engineering to precision mechanics, the Antikythera mechanism stands as one of the most astonishing examples of ancient technology. Discovered in a shipwreck off the Greek island of Antikythera in 1901, this intricate device, dating to the 2nd century BCE, is often described as the world's first analog computer, challenging prior notions of Hellenistic mechanical capabilities. Archaeological imaging, including X-rays and CT scans, has revealed over 30 precisely machined bronze gears, housed within a wooden case, covered in astronomical inscriptions. It calculated and displayed celestial positions, the sun, moon, and possibly planets, predicting eclipses and tracking the cycles of the ancient Olympic Games. Its complexity far surpasses anything else known from its era, demonstrating extraordinary craftsmanship. Historically, the mechanism provides crucial context for Hellenistic scientific advancements, particularly in astronomy and mathematics. It suggests that the theoretical knowledge of astronomers like Hipparchus was translated into highly functional mechanical devices. This object proves a level of mechanical engineering sophistication previously thought impossible for this period, forcing a re-evaluation of ancient Greek technological prowess. Theories abound regarding its precise origin and creators, with Rhodes, a center of astronomical study, being a strong candidate. The mathematical ratios of its gears accurately model the irregular motion of the moon, incorporating epicyclic gearing. This precision indicates a profound understanding of gear trains and differential gearing, concepts not fully developed in Europe until the Renaissance. Despite extensive research, aspects of its full functionality, display layouts, and how it was calibrated remain subjects of ongoing debate. Furthermore, finding comparable devices has been impossible. The Antikythera mechanism appears to be a singular advanced artifact, implying either a lost tradition or an exceptionally rare prototype. This uniqueness underscores the Tecnologia antiga e civilizações perdidas. We might never fully recover. Yet, ancient Egyptians achieved monumental feats without such complex devices. The pyramids of ancient Egypt, particularly those at Giza, stand as timeless testaments to an extraordinary level of architectural and engineering skill. Constructed over 4,500 years ago, these massive structures were built with a precision that continues to astound modern engineers and archaeologists. Their alignment, the sheer scale, and the apparent absence of wheeled vehicles or iron tools present a profound historical puzzle. Archaeological evidence shows the pyramid's cardinal point alignment is remarkably accurate, often within a fraction of a degree. The enormous limestone and granite blocks, weighing many tons each, were cut and fitted with incredible precision, often leaving gaps of less than a millimeter between stones. Investigations of quarry sites and causeways provide clues to stone extraction and transportation methods. From a historical perspective, the construction of the pyramids required immense organization, labor mobilization, and detailed planning. It reflects a centralized state with advanced administrative capabilities, capable of directing tens of thousands of workers over decades. This collective effort, guided by sophisticated architectural principles, highlights the scale of Egyptian Tecnologia antiga e civilizações perdidas. Current theories on construction methods often involve ramps, levers, and the ingenious use of sledges on lubricated surfaces for moving heavy blocks. Recent findings suggest specific ramp systems adapted to the pyramid's increasing height. The astronomical alignment points to a sophisticated understanding of celestial navigation and geometry, crucial for establishing the initial orientation and foundations of such colossal structures. However, the exact methodologies for raising the highest blocks and achieving such precise stone fitting across vast surfaces remain subjects of intense academic debate. No definitive blueprint or engineering manual has been found. This means our understanding relies on inference from archaeological remains and experimental archaeology, leaving certain aspects of their construction methods still shrouded in mystery. This leads us to consider other possible ancient power sources. Moving to a more controversial yet intriguing artifact, the Baghdad Battery, or Parthian Battery, discovered in 1936, has fueled discussions about ancient electrical knowledge. Dated to the Parthian era, around 250 BCE to 224 CE, this ceramic jar containing a copper cylinder and an iron rod suggests the possibility of rudimentary electrochemistry, sparking questions about ancient technology and lost civilizations. Archaeological evidence consists of three components: a terracotta pot, a copper cylinder inside it, and an iron rod suspended within the cylinder. If filled with an acidic electrolyte, such as vinegar or grape juice, this assembly could generate a small electrical current. Multiple such jars could potentially be connected in series to produce a higher voltage, a fascinating proposition for the period. Historically, if indeed a battery, its purpose remains speculative. Some theories propose its use in electroplating small gold or silver items, a technique known as gilding. Other suggestions include its application in medical treatments, perhaps a form of ancient electrotherapy, or even for ritualistic purposes to generate a mild electric shock. Evidence for widespread use, however, is absent. Scholarly analysis of the artifact's potential function varies. While some researchers have successfully demonstrated its ability to produce voltage through replication experiments, many historians and archaeologists remain cautious. They argue that the primary evidence for its use as a battery is circumstantial. Its construction could also be interpreted as a simple storage vessel for scrolls or occult object. The limitations of our knowledge are significant. We lack ancient texts or further corroborating archaeological discoveries directly describing or demonstrating its use as an electrical device. Without a clearer context or additional examples, the Baghdad Battery remains an isolated curiosity, a tantalizing hint of potential ancient electrical knowledge rather than conclusive proof of a lost technology. Yet other optical curiosities also provoke debate. Our journey through ancient technology now turns to optics, an area often overlooked. The Nimrud lens, discovered in 1850 at the Assyrian Palace of Nimrud and dating back to approximately 750–710 BCE, is a piece of polished rock crystal. This artifact sparks considerable debate among scholars regarding ancient understanding and application of magnifying or focusing properties. Archaeological examination confirms the lens is made from natural quartz, shaped into an oval and ground to a convex form. While crude by modern standards, its curvature possesses definite optical properties. It could certainly have been used as a magnifying glass or a burning glass, capable of concentrating sunlight. Its existence challenges the notion that sophisticated optics are a purely modern invention. Historically, the Assyrians were renowned for their intricate craftsmanship, particularly in jewelry and small-scale cuneiform writing. Some theories suggest the lens might have been used by artisans for detailed engraving work, or by scribes to aid in reading minute script. This indicates a practical application for technologia antiga e civilizações perdidas in specialized crafts, rather than purely scientific inquiry. However, the primary scholarly interpretation considers it more likely to have been an ornamental piece or a component of an elaborate inlay, rather than a deliberately designed optical tool. While it can magnify, there's no conclusive textual or contextual evidence indicating the Assyrians explicitly understood or utilized lenses for magnifying purposes as we do today. Its optical properties might have been incidental. The limitations of our understanding are clear. Without explicit descriptions or multiple examples of similar ancient optical tools, definitively classifying the Nimrud lens as a functional magnifying device remains difficult. Its unique status highlights the scarcity of evidence for ancient optical technology, suggesting it was either exceptionally rare or its specific uses are not well documented. Nonetheless, other ancient civilizations mastered observation through different means. Far removed from intricate mechanisms or monumental structures, the ancient Polynesians demonstrated a profound technologia antiga e civilizações perdidas in their mastery of oceanic navigation. Their ability to consistently explore and settle vast expanses of the Pacific Ocean, covering millions of square miles without modern instruments, represents an incredible feat of observational science and experiential knowledge. Archaeological and ethnographic evidence points to sophisticated voyaging canoes, often double-hulled, capable of long-distance travel against winds and currents. Crucially, their navigation relied on an intricate understanding of natural phenomena, star patterns, wave swells, prevailing winds, cloud formations, and the behavior of birds and marine life. This comprehensive knowledge formed their navigational toolkit. Historically, Polynesian wayfinding was a highly refined discipline, passed down through generations of master navigators. They memorized vast amounts of celestial data and observed subtle ocean cues, essentially carrying complex mental maps. Their journeys connected isolated island groups, creating an expansive cultural network across the Pacific, a testament to their deep ecological intelligence. Theories on their methods include star compasses, mental constructs of directional bearings based on rising and setting points of stars, and stick charts, which visually represented ocean swells and their deflections around islands. Their ability to detect land over the horizon by observing specific cloud formations or altered wave patterns showcases an empirical science developed through centuries of voyaging. Despite successful modern reenactments of ancient voyages, the full depth of their traditional knowledge is difficult to reconstruct, as much was oral and highly specialized. Colonial influences disrupted these traditions, leading to the loss of many specific techniques and mnemonics. This limitation underscores the fragility of knowledge transfer across generations and the profound impact of cultural disruption, urging us to reflect on these lessons. Our journey through Tecnologia Antiga e Civilizações Perdidas reveals a profound truth. Innovation is not exclusive to our era. From Roman concrete's self-healing properties to the precision of the Antikythera mechanism, ancient peoples often possessed insights and engineering solutions that continue to amaze and challenge modern understanding. Their accomplishments provide invaluable lessons for today's technological landscape. The durability of Roman concrete offers inspiration for sustainable building materials, encouraging biomimicry and long-term resilience over rapid degradation. The water management systems of the Nabateans and the Indus Valley demonstrate ingenious solutions to resource scarcity, highly relevant in our changing climate, urging us to reconsider decentralized, environmentally harmonious engineering. The Antikythera mechanism reminds us that complex computational devices have ancient roots, showcasing human ingenuity in developing predictive models. Polynesian navigation underscores the power of empirical observation and deep ecological understanding, contrasting sharply with our reliance on satellite technology. These historical precedents offer alternative paradigms for technological development. While we acknowledge the limitations of our knowledge, the undeciphered scripts, the lost oral traditions, the unique circumstances of their discoveries, these gaps should not diminish the impact of what we do. No. Instead, they serve as a powerful reminder of the cyclical nature of innovation and the possibility that even advanced knowledge can be lost to time, waiting to be rediscovered. Ultimately, studying these ancient technologies is more than an academic exercise. It's a vital connection to human potential. By understanding the brilliance of our ancestors, we gain perspective on our present challenges and inspire future solutions. What ancient, transient technology and lost civilizations do you find most fascinating? And what lessons do you think they hold for our future? Share your thoughts in the comments below, and don't forget to subscribe for more historical deep dives.